And welcome back as we continue our cosmic journey. We, of course, have had some good conversations about quasars. Let's go ahead and see how they relate back to supermassive black holes. So as we begin our hunt for quasars, it's very common to kind of have a model that we can use as well as active galaxy nuclei and examine the common characteristics. Quasars, of course, are hugely powerful, emitting more power in radiated light than in all the other stars in a galaxy combined, but are only about the size of our solar system. Now, some quasars are observed to be shooting out pairs of straight, powerful jets of radio and gamma ray radiation at close to the speed of light, in a relatively tight beam, pushing it all the way out to distances that are far beyond the galaxies that they live in. And we know that quasars can't be powered by nuclear fusion. Quasars also were much more common when the universe was young than they are today, and must have been able to form in the first billion years or so after the universe began to expand. As proof of the existence of black holes accumulated over several decades, it became clearer and clearer that only supermassive black holes could account for all the observed properties of quasars and AGNs. The evidence now shows that most elliptical galaxies and all spiral galaxies with nuclear bulges have black holes at their centers. Now, the amount of energy emitted by material near the black hole depends on one or two things. First, the mass of the black hole and the amount of matter that is falling into it. So what's some observational evidence that we have for black holes? Well, if we want to prove that a black hole is present at the center of a galaxy, we must demonstrate that there is so much mass crammed into such a tiny volume that no normal object could possibly account for it. So if we assume that the energy emitted by quasars is also produced by a hot accretion disk, then the size of the disk must be given by the time the quasar energy takes to vary. Now, for our quasars, the emission in visible light typically varies on timescales anywhere from about 5 to 2,000 days, limiting the size of the disk to that many light days. The next challenge then is to effectively weigh the central mass in a quasar. Now, in the case of our own galaxy, we use the observations of orbits of stars very close to the galactic center, along with Kepler's third law, to estimate the mass of the central black hole. In the case of distant galaxies, we cannot measure the orbits of individual stars, but we can measure the orbital speed of the gas in the rotating accretion disk. The Doppler effect is then used to measure radial velocities of the orbital material, and after we've done that, we are able to derive the speed with which it moves around. But do we have to accept that black holes are really the only explanation of what lies at the center of these galaxies? We've been saying, hey, there's a supermassive black hole here, but what other evidence do we have? What could be a possible alternative for such a small space other than a giant black hole? Well, really, the only other thing that we can think of that could be a good alternative would be stars. But if we want to explain the masses in the center of galaxies without a black hole, we would need to put at least 1 million stars in a region that's about the size of our solar system. Well, in order for these stars to fit, we'd also have to make sure that there's at least 2 star diameters between each of them. Collisions between stars, though, at this distance would happen all the time. And what we would find is that these collisions would lead to mergers of stars, and very soon, one giant star that would form and then would eventually collapse into a black hole. So let's take an example of the energy reduction that happens around a black hole. Now, in a galaxy, a central black hole with a strong gravity attracts matter orbiting in the dense nuclear regions. This matter spirals in toward the spinning black hole and forms an accretion disk of material around it. Now, as that material spirals ever and ever closer to the black hole, it accelerates and becomes compressed, and eventually starts heating up to temperatures that are millions of degrees. Now, such hot matter can radiate prodigious amounts of energy as it falls in toward the black hole. Dropping things from far away is then therefore going to be much stronger gravity of a black hole that's more effective in turning the energy released by infall into other forms of energy. Now, the energy of material falling toward a black hole can be converted to significant amounts of electromagnetic radiation. For example, we have a dense blob of gas moving through a thin gas at a high speed. It will tend to heat up as it slows down by friction. And as it slows down, kinetic motion energy is then turned into heat energy. So gas approaching a black hole will do something similar. It'll heat up and glow where it meets other gas. But this gas, as it approaches the event horizon, will reach speeds of about 10% the speed of light, and even more and more as it reaches no more than 1500 Kelvin. Indeed, gas near a supermassive black hole reaches a temperature of about 150,000 Kelvin, which is about 100 times hotter than a spaceship returning to Earth. Now, what we also find is the matter here can get so hot, in terms of millions of degrees, that it actually can radiate out X-ray energy. Now, the amount of energy that can be liberated in this way is enormous, releasing nearly 32% of the mass as energy. Now, most black holes don't show any signs of quasar emission, but can be woken up by being roused with a fresh supply of gas. Now, our own Milky Way black hole may have had such a quasar just a few million years ago. In this image, we see, of course, two giant bubbles that extend about 25,000 light years above and below the galactic center of the Milky Way, and you can see that they are currently emitting X-rays. So, were these produced a few million years ago when a significant amount of matter fell into the black hole at the center of the galaxy? Well, astronomers are still working to understand what remarkable event might have formed these enormous bubbles that we just looked at. The physics required to account for the exact way in which the energy of infalling material is converted to radiation near a black hole is far more complicated than anything we have the ability to discuss here in this class, and it's actually going to require us to probably utilize computer simulations. Next, let's talk about the radio jets that we can get from black holes. Now, quasars can also have long jets that glow with radio waves, light, and sometimes even X-rays. And what we find is that these radio jets extend far beyond the limits of the parent galaxy. So, for example, can we find a way for our black hole and its accretion disk to produce these jets of energetic particles as well? Well, many different observations have now been traced these jets to 3 to 30 light years of the parent quasar or galactic nucleus. While the black hole and the accretion disk are typically smaller than 1 light year, we nevertheless presume that if the jets come this close, they probably originate in the vicinity of the black hole itself. Another characteristic of these jets is that we need to kind of explain that these jets still contain matter, but that matter is moving close to the speed of light. And why are energetic electrons and other particles near a supermassive black hole ejected as jets? And often they are going into oppositely directed jets rather than necessarily, let's say, all directions. For example, like our sun radiates energy out in every direction rather than simply just pointing at Earth. In order for us to really understand this, we have to use theoretical models and supercomputer simulations when a lot of material whirls and we're in a crowded black hole accretion disk. And there's no real agreement that we currently have on exactly how jets form, but it has become clear that any material escaping from the neighborhood of the black hole has an easier time doing so perpendicular to the rest. Perpendicular, of course, means that it's going to be at a right angle. And so these two drawings are going to show what the accretion disk might look like around a large black hole. In image A, we of course can see a thin accretion disk. And in image B, we see a much fatter accretion disk. This, of course, is the type needed to account for channeling the outflow of hot material into narrow jets oriented perpendicular for the disk.